All right, hi everyone. My name is Kate Goldenring, and as Kovis mentioned, I'm a software engineer at Fermyon, where we do a lot of work around creating developer tooling and a cloud for running serverless WebAssembly. So that's really what I'm going to be talking about today, is what does WebAssembly look like in a serverless context, and why should you care from a context of sustainability? So I first want to start off by level setting on our definition of serverless. You can think of it as two different definitions. One, serverless is a type of application, one where you're building event-driven handlers that, such as an HTTP request, maybe it's a message entering a queue, maybe it's a change in a bucket. Serverless functions tend to be ephemeral, so they're short-lived, and there's shared nothing between requests. So in its purest form, your serverless instance should be completely isolated from the next request even. And like I mentioned, they're completely stateless, and so that is part of when you're architecting those serverless applications. The other side of what serverless is that it is a development model. So one wherein, as a developer, you can focus only on the business logic, and then your platform handles configuring those data resources, such as your key value stores and your databases, and so on. And you may have heard functions as a service when you think of serverless, and that's totally fine as well. So I mentioned some of the reasons we might be interested in serverless, and that is focusing on business logic, which can improve the developer productivity that you get. But there's also another part of serverless that's really important, and that's that if you have this fine-grained ability to scale based on function, then you can actually have faster scaling and more precise scaling. And beyond that, you can also get more fine-grained isolation. So your isolation level is now on the function level and the request level, rather than on the broader microservice level. And what this leads to is that if I can scale more precisely, I can scale all the way back down when I'm not having requests issued to that function. You can actually have increased density, which therefore you can have better utilization of your hardware. So you can do more with less hardware. And I really want to focus on these last two, because when you can do more with less hardware, you get cost savings, which is great for our companies, but if you care, you also reduce your energy footprint. And I want to talk a little bit about a calculation we can use to discuss energy footprints, and that is software carbon intensity. And this is an equation that was created by the Green Software Foundation, and all it does is it measures the amount of carbon per functional unit of your application. And a functional unit could be, say, like processing an order. And if we expand out this formula, software carbon intensity, the carbon part of it we can think of as the energy consumed by your function or by your system at large, multiplied by the location-based marginal carbon intensity. And so we know that we can region shift where our applications are running and get benefits of using more renewable sources of energy. And then we add to that the embodied emissions. So these are the emissions that are created from producing the hardware that our software is running on. And that's, once again, per functional unit. And this is my favorite composition of the formula. It's reduced but somewhat expanded. And that just is that software carbon intensity is your operational emissions, so the emissions of your software, plus your embodied emissions, the emissions of your hardware per functional unit. So we want to reduce the O and the M in order to achieve better software carbon intensity. And we know the ways we can do some of these things. To simplify we can use less energy to do the same function, and we can use less hardware to do the same function. And like I mentioned, you can also change where your applications are running. And if we want to do more with less hardware, well, like we were saying, we need to be able to put more tenants on the same piece of hardware. So we need to achieve greater levels of multi-tenancy. And multi-tenancy is just running multiple applications in a shared environment. And it assumes that these tenants are comfortable running next to each other. So you have to have a strong isolation mechanism so that you feel comfortable with your application code running next to another user's application code. And we also can assume that these tenants are uncorrelated. Their applications will receive different traffic, and that they are truly different use cases. And what multi-tenancy does when it's achieved fully is that it brings the cost of your system closer to the value you get out of your system. So you can measure the cost of a system by the short-term peak traffic that your system gets. So essentially, you need to provision for the peak, because you have to handle that. While the value you get out of the system is the average use over time. So you can even think of this as in the sense that we have billing models that are a certain amount of requests per month that you're limited to. However, if you send all those requests on a Tuesday and so is everyone else, your infrastructure needs to be able to handle that. And I actually learned about this concept of closing the peak to average gap from Mark Brooker, who is a distinguished engineer at AWS, and he actually was one of the original authors of AWS Lambda. And he has a really good article about the economics of multi-tenancy that I highly recommend reading, and I linked it there. And after reading that article, I kind of wanted to visualize this for myself. So I naively created a random load for 2 different tenants. So a random number between 1 and 10 that represented a load, and did that over time 0 to 10. And I graphed it out. And those are those bottom 2 curved lines. And then the top curved line shows the sum of load at any given point for those 2 tenants. And then the top horizontal line is the peak sum at any point, so what I would have to provision for. And then the bottom line is the average load at any given time. And you can see that the peak is 1.7 times higher than the average in this system here with 2 tenants. Now, if I were to add 2 more random amounts of load, you can see that now the peaks and the troughs are starting to balance out between the tenants, and that we're having flattened usage. And what that did at the top of this graph is it brought the peak closer to the average. Now it's only 1.25 times higher. So I'm actually using and provisioning hardware that's closer to my needs. And all this says that if I have a solution where I can start up functions only when they're needed, tear them down immediately, and truly am using things only when I need, and I achieve this and I add a ton of different tenants that are uncorrelated to my system, I should be able to have a very high level of hardware utilization. So serverless should be the solution to everything. However, we have a problem with serverless today, and that is a startup problem. So if you've used serverless solutions, you know that when you execute a request on a function, it's not actually starting up then, running and returning your request. In reality, it's been pre-warmed. And that's because the underlying functional units behind that technology cannot start as fast as we would like. So because cold startup times can be 500 milliseconds up to a second, we have to pre-warm these instances. And what happens is that the amount of time to start up that function is actually longer than the amount of time we execute it. So we're wasting resources and using resources before we actually want them. And if we look at some of those specific implementations that the technologies that are being used, one of the most popular, Lambda's, AWS Lambda, it uses the Firecracker MicroVM. They put in their documentation that cold starts can be between 100 milliseconds and a second. But they reassure you saying that only 1% of function calls will get cold starts. And that may be reassuring from the usage and the latency perspective, but to me that's really unreassuring because someone has to pay for that cost behind the scenes of all those pre-warmed instances. And that means that we're not achieving the hardware utilization we want. Other serverless solutions use containers. Microsoft Research put out a paper where they discussed Azure Functions and how it's becoming prohibitively high to run some of these solutions because they're keeping these containers warm all the time because they're getting this level of traffic where it's about 1 per minute, where they always have to have it pre-warmed and they can never actually really shut it down. And so they're not really achieving what they wanted out of that serverless solution either. And we see this on Kubernetes as a whole. The SysTig 2023 Cloud Native Security Report and Container Usage Report showed that about, on average, 69% of cores in Kubernetes clusters were unused. So we have a really low utilization of our CPUs in our clusters. And that's really, that's a big problem because just because we're using 31% of our CPU does not mean we're only using 31% of the power of those nodes. And that's because there's a non-proportionality of energy consumption. So even if your servers are idle to up to 10% use, that actually is consuming 30 to 60% of the power of that server. You can think of this almost as a bus. Like as long as you're driving the bus, you're burning gas, and as you add more people to the bus, you're only marginally burning more gas due to weight. It's kind of similar with our servers. So we really want to achieve higher levels of utilization of our servers, 80, 90% if we can, and we're not achieving that right now with our current solutions. And we've been doing better at this over time. So I just said we're not doing well, but we have been doing better. And that's because we've been increasing our multi-tenancy over time through evolutions in cloud computing and waves of cloud computing. So we started with virtualization, with hypervisor technology. We're now able to run multiple tenants on the same piece of hardware. Then with virtualization, we're still building monolithic applications. Then containers came about. With that, now we're building microservices where we can scale services independently. There's some level of isolation, And then with MicroVMs, now we're able to have our first serverless solutions where we feel like we can scale on a function level, but we're not getting the performance that we'd like, as we were mentioning. And now we have WebAssembly, which can run outside of the browser as of 2019, and that's kind of where I want to talk about where we can actually achieve the goals we have for serverless. So to start, what is WebAssembly? Its name is super unhelpful. WebAssembly did originate in the browser. It was a way of compiling more languages. It was a way of writing web applications in more languages than JavaScript. And because of that, is actually a portable compilation target, is one way to think of it. I can take my favorite language of choice, whether that's Go, Python, Rust, JavaScript still, and compile that to a Wasm artifact, so just a .wasm file. And now I can take that, that binary and run it pretty much anywhere I can put a WebAssembly runtime. So I could run that on my MacBook. I could run that on a Windows VM. I could run that on the edge. And it's this really compact, portable binary. And so what that does for us is we no longer have cross builds, which is one other side sustainability benefit. We have this one application that we can run anywhere. Beyond that, the WebAssembly components are incredibly small. So while an Express.js container may be 200, 400 megabytes, the WebAssembly equivalent, 2 to 3 megabytes, which is also great for sending distributing these WebAssembly components. We have to talk about security because we're talking about serverless. WebAssembly has a very strong sandbox environment. So WebAssembly components are sandboxed in linear memory and beyond that, by the WebAssembly runtime. And beyond that, WebAssembly has a concept of capability-based security. So a WebAssembly component can only have access to resources it has explicitly been granted access to. So by default, no outbound HTTP requests, no accessing any files, no access to resources like key value stores and databases and all of that. And that may sound very prohibitive, and I'll talk a little later about the developer tooling out there that makes it really easy in TOML to express what you have access to and configure that in the runtime for your specific application. But it speaks to also the really default, very strong security posture of WebAssembly. And then finally, for startup time, WebAssembly components can start in less than a millisecond. So startup to tear down, less than a millisecond. So we truly can start per request an isolated instance of your function and tear it all the way down and return your response in very, very fast times. And so I mentioned that what's the developer tooling where I can get started doing this and configure all the resources my WebAssembly components can talk to. And the open source project I work on is called Spin, and it aims to make building these serverless event-driven WebAssembly applications a smooth experience. And beyond that, it also makes distributing it to your clusters, to your serverless cloud, also a seamless experience. So I want to go ahead and do a quick demo to show how fast that experience is. So I have the Spin CLI downloaded here. And you can see there's various subcommands. You can also see we have plugins. I'll mention a little bit more about that in a second. But the flow is really just a spin new, and now you can scaffold an application of your language of your choice. I'll go with JavaScript just because more JavaScript developers than anyone else, but you could choose Go, Rust, etc. And you'll just name your application. Go hello spin, choose some description, optionality. And then by default, it's going to assume you want your application triggered by an HTTP request. That doesn't have to be the case. We also support other triggers, which I'll mention. But within that trigger, you can also specify what specific route you want it to be triggered on. So I'm just going to say the hello path. And then you'll see now my application has been scaffolded. We can look into what source code has been scaffolded for us. And it's just simply a simple handle that you can modify that just takes in an HTTP request and returns a response. And we can just change this to whatever we wish it to be. So let's just say hello from DevOpsDays. And then also I want to show this is where you configure your Spin application. This is where you say what it has access to. So you can see here it's not allowed to make any outbound requests. You can also add lines here for key value stores, SQL databases, large LLMs, so on. And you can see here I also only have one component here. So we have just our hello Spin component, you can add n many components here. So one spin listener for all of your components. So now we're ready to first install our dependencies. So this is the same for whatever language tooling you have. There'll be a different flow for installing your dependencies. And then now we're ready to build our application. Spin build. And we'll see that now we have our WebAssembly component. And now the next step, if I want to go ahead and run it locally, just a simple spin up. And I can go ahead and hit that endpoint. And, oh, hello clear is not what I meant. And hello from DevOpsDays. So that's just a quick example of how quick the flow is for getting started with Spin. And we just had that demo. And as I mentioned, there's other triggers. So we saw an HTTP trigger. You can also have your Spin application be triggered by a new message in a Redis queue directly by a command. So this is helpful for init containers in Kubernetes. MQTT, you can subscribe to a specific topic and have that trigger your Spin application. Or you can even build your own. I mentioned the plugin system, so you can Spin plugin install your new trigger. MQTT was actually contributed by a user because they wanted to use MQTT as a trigger for Spin. So definitely easy to expand it for your use case. And then now that we have our Spin application, where can I put this? What infrastructure can this run on? So we saw locally. Edge is a great solution also because we have these small sizes of our applications. Fermi Cloud, which is our hosted serverless platform, we use Nomad to orchestrate. But we also recently at KubeCon Paris announced SpinCube, which is the conglomeration of 4 open source projects by various companies, namely Microsoft, us at Fermion, SUSE, and Liquid Reply, that makes it easy to run Spin applications now on your Kubernetes cluster. So I want to talk a little bit more about that one. These are the 4 projects, and if we look quickly at the design of all of that, starting from the bottom, you have your containerd shim. So how can we run WebAssembly on nodes? This handles that. So it uses run WASI to execute your WebAssembly applications on your nodes alongside your containers. And we have a runtime class manager, which is a Kubernetes operator that quickly enables installing this shim on your nodes that you want to also support WebAssembly. And then above that, we have our Spin operator, which listens for our Spin app custom resource and will deploy your Spin apps to your cluster. And it also has all of the Kubernetes native additions that you can make, so horizontal pod auto-scaling, secrets, volume mounts, et cetera. And then you can use our SpinCube plugin to go from what we just had of our Spin application to now deploying it to your cluster. So I'm going to go ahead and show that. So if we go back to where we were working on our Spin application, I'm realizing this might be a little small. So now that we've built our Spin application, you need to push it to a registry. And you can bundle a Spin application or just a Wasm file in as an OCI artifact. So I'm going to go ahead and do that. We're going to use ttl.sh. If you haven't used it before, it's great for demos and just quickly pushing something up to a registry. It's an ephemeral image storage. And so I can go ahead and push my Spin app that I just built up to a registry, and this is packaging it up, like I mentioned, as an OCI artifact. It's not a container. We're using OCI as a distribution mechanism. And once I've pushed that to my registry, I now can apply this to my cluster using SpinCube. So SpinCube is another plugin, like I mentioned, and we'll just say what we exactly are scaffolding into our cluster. And you can also specify how many replicas you want of it. I'm just going to say 1. And before I apply that to cluster, I just want to show what the custom resource looks like. So this is saying this is the image that I want to use for my Spin application. This is how many replicas I want. This is the executor I want. And this is where I was saying you can extend it to do other things like secrets and attach variables and environment variables. And Spin has its own concept of configuration variables and so on. And now I can go ahead and apply this to my cluster. And I didn't show, but let me just first show you what my cluster looks like. It's a 4-node AKS cluster. And if we go ahead and get our pods, we can see that our spin app is now running. I also have another application running there that we may get time to demo. And now that it's on my cluster, I'm going to go ahead and just port forward. And we can go ahead and hit it again. And once again, we're getting our response, but now it's running on a cluster. And that was just really simple to push up just by applying our custom resource. So I wanted to share a case study where someone basically did this. They had used a containerized serverless solution previously. This is the Zeiss group, and they switched and wanted to see, okay, what if I switch to WebAssembly? Will I see the benefits of higher density and reduced costs? And so if you want to look at their exact case study, there's a GitHub repository there where you can reproduce it. But essentially, they were able to cut the cost of their compute by 60% by switching to WebAssembly. And a part of that percentage was because they were able to switch the architecture of their nodes. So previously they were using x64 and they were able to switch to ARM because with WebAssembly you can run those same applications anywhere, so they can continue to change their mind. If they want to go back to x64, they don't have to rebuild anything. So that is one of the added benefits of switching to WebAssembly. I wanted to point out one thing about my demo, which is that we saw one function for that one spin app, which isn't super realistic. So I wanted to show another example, which is a fun game that we've built called Finicky Whiskers, which is basically we say the world's most adorable manual load generator. You try to feed a cat as much as you can in 60 seconds. And it consists of 7 different WebAssembly components that each talk to different resources, such as a key value store to write the current score, or pull the latest score, a SQLite database to associate users with high scores, and then other components such as one that can just reset the game if we need to get a clean slate. And if we just look real quick at what that spin application manifest looks like, you can see that instead of 1, now we have 7 different components within that same application manifest where we're specifying, you get access these key value scores, these databases, and you specify that on the granularity of a specific function. So let's go ahead and try it out. So if I was going to show it on our Kubernetes cluster, but I think our Redis instance is down. But the reason I wanted to show it there is that we actually have a horizontal pod we've enabled the horizontal pod autoscaler on it. So if we had enough people, it would be cool to see if we could scale up the number of instances based on actually feeding slats a ton. But instead, I'm going to show you the version that we've deployed to Fermyon Cloud, which is at finickyWhiskers.com if you're interested in seeing it. But I'll just quickly play, and you get to choose if you're a dog person or cat person. I will confess, I am a cat person. And the way it works is you just start feeding Slats the cat as much as you can, exactly what Slats wants, when Slats wants it. And you can see that every time I am feeding Slats, I'm actually firing off multiple different WebAssembly instances to update the tally, update the scoreboard, and then at the end, we'll update the high scoreboard, and that just goes for 60 seconds or more. But that is our fun way of showing just how fast WebAssembly is. Every single time I clicked that, I created a new instance in linear memory, I executed it, I started it up, and I stopped it. For every single click, we did that 3 times for different functions. And with that, I just wanted to share some resources if you're interested in learning more about SpinCube. That will also get you to Spin if you want to learn about Spin itself, if you're more interested in running that on a different platform, locally at the edge, etc. And we may have a little time for questions.